Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a structural simulation together step by step and follow along with the practice example. The topic of today's tutorial is understanding modal analysis. Every structure has its own natural frequencies at which it tends to vibrate. When the excitation frequency matches a natural frequency, the vibration can increase significantly. This is called resonance. Dynamic analysis is used to evaluate resonance and reduce the vibration response of a structure. Modal analysis is the first step in dynamic analysis. It identifies natural frequencies, mode shapes, and mass participation factors. A natural frequency is the frequency at which a structure naturally vibrates. A mode shape describes the deformation pattern at each natural frequency. A mass participation factor indicates how much each mode contributes to the response in each direction. In summary, modal analysis identifies the fundamental vibration characteristics of a structure and provides the basis for dynamic analysis. In this example, we will perform a modal analysis of a monitor structure. The purpose of this analysis is to identify the fundamental vibration characteristics of the monitor structure. The analysis model uses alloy steel and PC materials. The bottom support is fixed, and a 1 kilogram mass is applied to the monitor. In the results, we will review the mode shapes using the animation. We will also use the mode table to review the natural frequency and mass participation factor for each mode. This allows us to identify at which frequencies the monitor vibrates and how it deforms in each mode. Now, let's begin the tutorial. First, click the New button in the upper left corner to open a new project. Then verify the unit system and click OK. Now, let's import the model. Click Import in the Geometry tab, select the example model, and click Open. Once the model is loaded, right-click in the workspace and select Hide All Guides. Next, let's define the material and property settings. Right-click Materials and create an isotropic material. Select the library material as shown. Material properties such as Young's modulus, Poisson's ratio, and density will be assigned automatically. Move to the Properties tab, create a 3D property and assign the material. This example uses two materials, so we need to create two properties. Before generating the mesh, apply seed control to the bracket region where stress may concentrate. This creates a finer mesh in that area. Then, right-click in the workspace and select Show All Geometries to display all geometry. Next, let's generate the mesh. Click 3D in the Mesh tab to open the Mesh Generation tool. First, apply a 6 nn element size and the PC property to the two PC parts. Select the model geometry and enter the desired element size. For the remaining parts, apply a 3 nn element size and the alloy steel property. Next, we will create rigid elements to apply the condition. Open the rigid element function and change the selection target to face. Select the four faces of the monitor to create the rigid element, and then click Apply. Next, select the target geometry as face and choose the bottom surface of the monitor. Change the master node selection option to vertex, select the reference vertex, and click OK. Then, open the concentrated mass function and enter 1 kilogram as the omitted mass of the monitor. Now, let's define the boundary conditions. Set the object type to node. Then select the master node at the bottom of the monitor and apply a fixed condition. Next, let's create a welded contact condition. In the Structural Static Analysis menu, click Contact Condition and then select Auto Contact. Set the contact type to welded, select all bodies, and click OK. This will create welded contact conditions between all parts. Now that the analysis setup is complete, let's create an analysis case. In the Analysis tab, go to Single Analysis. Set the solution type to Modal. Verify the number of modes to be extracted. Click OK to create the analysis case. Right-click the analysis case, then select Solve to run the analysis. Once the analysis is complete, let's review the results. First, double-click the displacement result for each mode. Click the play button to view the mode shape animation. Next, open the eigenvalue analysis result table. Review the cycles value for each mode. Then review the percentage modal effective mass results. The mass participation factor exceeds 90% in all translational directions. To continue with the frequency response analysis in the next example, save the model using the Save As function. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.